Hello, welcome back. We have been talking about primality testing using randomized algorithms. In the first version, we are talking about Fermat-Euler's theorem based idea, meaning we randomly generate a number a and check whether a power n minus 1 mod n is not equal to 1. If that is true, we found that n cannot be prime. Okay, that's something we talked about in the last two segments. But there is still a remaining question. Okay, what is the probability that a composite number is wrongly reported as a prime? Okay, in order to answer that, I'm going to build a few mathematical propositions and lemmas along the way now. So let me start with the very first proposition. So the proposition is as follows. Suppose you are having a group G with you. Okay, suppose you have a group G. Okay, group means a set with a bunch of properties we talked about earlier, like closed, associative, identity, and there is an inverse for every element. These are the fundamental properties of a group. And in cryptography, we almost often deal with finite groups. That means the set G is a finite set. Okay, and suppose you also have a subset, non-empty subset. Okay, let's call that non-empty subset to be H. Okay, so the proposition I wanted to show to you is this. Suppose you take any two elements in this subset. Okay, let's say this is element A and element B. Okay, and let's say you multiply A and B and you will get AB, which is an element again in H. Okay, that's called the closure property. Okay, if the proposition is as follows: if AB is also an element in the set H, right, then we claim that H is a subgroup. Okay, implies H is a subgroup. Okay, subgroup means a group which is a subset of another group. Okay, so we claim H is a subgroup. So we need to prove this, of course. How do we prove this is a subgroup? Subgroup means we need to prove that it satisfies all the properties of a group. Okay, first property that we need to prove is closure property. Luckily, the closure property is true. We assumed that it's true, right? See here, there's an if condition here. We assumed that any two elements, if we multiply, the result is also a group element. So closure is true by definition given to us. Okay. What about associative property? Associative property is obviously true because elements of H are all elements of G. So you could multiply elements in any order you want using the same multiplication operation defined for group G. Okay, so associative is true. What about inversion identity? Let me start about identity first. You take an element A, okay, and you keep multiplying it. Okay, what is the assumption we made? If you multiply A with any element, the answer is also the element of the group H or set H. We are not yet proved that H is a group. So what if I multiply A order of G times? Okay. Now we must be able to recall one of the theorems we talked about. If you take any group element and multiply it order of the group times, the answer will be 1. Okay. Let me now use a symbol M to denote the order of the group G, which means the number of elements in the group G is M for a moment. Okay. So what can we say now? We can now plug the M over there and we get A power M is equal to 1. Okay. Okay, so is 1 part of H? Obviously, because we multiply A M times, right? A into A M times, we get 1. But we are given the assumption that any two elements, if you multiply, the answer is part of the set H itself. Therefore, 1, how did we get 1? We get 1 by multiplying A M times A into A and so on. And we know by definition, this answer is, this number 1 is part of H because the closure is assumed. Okay, so we multiply A M times, the resulting number, which is nothing but 1, is also part of H. So 1 must be part of H. Okay, now we need to prove that every element A in the set H has a multiplicative inverse. How do we do that? We can take this identity and rewrite it as follows. We can take A and we take A power M minus 1, right? Which is nothing but, you have power 1. Because of the exponent, you can add. So what does it mean? It means that the inverse of A is nothing but A power m minus 1, otherwise you can't get 1. So A inverse is nothing but A power m minus 1. And we already proved that A power m minus 1 is a group element. More specifically, is an element of the set H because of the closure property. If you treat A and B are equal, you keep multiplying A m minus 1 times, the answer will be part of the set H, okay, which is nothing but A inverse. Therefore, the argument is if we take A inverse is also an element in the set, okay. So what are the things we proved? We proved that by definition, H is closed because we assumed that multiplication is part of the result of multiplication is part of the set H, okay. We already know identity, we proved it identity. We also proved multiplicative inverse for every element, every non-zero element. And associative is trivial because H is basically a subset of G. If multiplication can be performed in G, it should also be performed in H using associative property. So no problems whatsoever. Okay, so what is the conclusion now? The conclusion of this segment is that if you multiply any two elements and the result is also part of the set H, then the set H is nothing but a group, okay? That's basically what I proved, all right? In the next segment, I will talk about what is the max size of the group H, okay? How many elements can there be at most? We will use those theorems to reason about the primality test, okay? Thank you.